Uh, okay, so who is recording now? Okay, great. So a ring is an abelian group together with an associative multiplication, which respect the abelian group structure. So there's this distributive law holds for all elements from the ring. And a ring is called as a K algebra if K is a field, if it's an additional vector space, and the multiplication is a bilinear map. There are also algebras over rings, and we'll define them later. We'll talk about them at some moment. A ring is called unital if it has an identity with respect to the multiplication. And the ring is called a division ring, or a Kane algebra is called a division algebra if any non-zero element is invertible. So let me give a few examples of rings and algebras, and we'll have a lot of them afterwards. Any field is a ring, and any algebra over itself is a commutative division algebra. A ring is a division algebra because every non-zero element is invertible. It also is commutative because a field is commutative by definition. All integers is a ring. No, natural numbers is not a ring because it's not a group with respect to the summation. It's a semigroup. Quaternions, which we considered the last time, is a non-commutative example of division algebra. All non-zero quaternions are invertible. Let's take an algebra or ring and consider polynomials whose coefficients are elements of the ring or the algebra. Then it's again a ring and an algebra respectively. And if it's commutative if only if the ring R or the algebra R are commutative, because the generators of the polynomial algebra are commutative by definition. For any set X, the space of functions on X with values in some ring algebra or algebra under the point mass multiplication is again a ring and an algebra. And we see a more general example of this, which is the direct product of rings and algebras. And it's commutative if and only if R is commutative. If R is an algebra or a ring, then matrices whose entries are elements of R is a ring or an algebra. And it's commutative if and only if n equals to 1 and R is commutative, of course. If R is commutative, not necessarily matrices n cross n are commutative. For any vector space over or a field K, endomorphisms over K, just K linear maps, is a K algebra. A subring or a subalgebra is a subset which is closed under both operations, the summation and the multiplication. It is a ring and algebra itself. If you have a possibly infinite collection of rings and algebras, the Cartesian product and the direct sum are rings or algebras respectively. And we'll see a little bit later how it works. A left-right ideal, by definition, is a subring or a subalgebra, which is stable under the left or right multiplication on all elements from the ring on the algebra. If it's right and left simultaneously, then it's called a two-sided ideal, or later we'll call just an ideal. A morphism of rings or algebras, it's as usual. Morphism is some map which respects the algebraic structure. In this case, it must respect the summation, the additive structure, and the multiplication, the multiplicative structure of the ring or an algebra. In the case of algebras, of course, it should be also K-linear. If you consider all rings or algebras, then it's a category, and the objects are rings and algebras, and morphisms are those defined above. The kernel of any morphism is an ideal, and the image of any morphism is a subring in the target. An ideal is called proper if it does not coincide with the whole ring algebra. Non-trivial if it is proper and non-zero, so something is between 0 and the whole algebra or ring. A non-zero ideal is called minimal if it does not strictly contain any other non-zero ideal. A non-trivial ideal which is not strictly contained in any other proper ideal is called maximal. Of course, if we relax the condition that it's non-trivial, then, for instance, the algebra or ring itself is maximal, but it's forbidden. A ring or an algebra is called simple if it does not have ideals other than 0 itself. so does not have any non-trivial ideal. A semi-simple algebra is a direct sum of simple algebras. An algebra is semi-simple if and only if it's the direct sum of its minimal ideals. It's a statement which has a very easy proof. So if you take the sum of minimal ideals, if you have the sum of simple algebras, if every summand is a minimal ideal, of course, because first of all, it's an ideal by definition. Second, it has no smaller ideals inside except 0. And if you have the sum of say two ideals or some collection of ideals, then for any two ideals, the product, the intersection of them, the intersection of them is 0. And if you consider the product of two elements from two different ideals, then by definition, it must belong to the intersection which is 0. So they do not intersect, and product of them is 0. So it means that the direct sum of ideals is the same as the direct sum of algebras. If the ideals are minimal, then the corresponding algebras are simple. So in the case of rings, there is a definition of a module which is somewhat different because we relax the property of being a vector space. For any abelian group, the set of its endomorphism is a ring with respect to the nature of summation and composition of maps. We call an abelian group a module over ring R if there is a morphism from R to endomorphisms of M. So it means that for any x, for any A from R, we have a morphism of the corresponding abelian group M. So a morphism property means that it respects the sum. So this is the first line. And the second line means that indeed we have, the second part of the first line and the last line means that we indeed have a representation of R inside endomorphisms of M. A morphism of modules over a ring is a morphism of the corresponding abelian groups which commutes with the action of the ring. So, for instance, there is the most general, the easiest example. If the ring is a free is Z, then every abelian group is a Z module, because for every abelian group we can multiply with the number. So n times an element x is just x plus x n times. So there is always a representation of Z. So for this means that abelian groups is the same as Z modules. If the ring is not that simple, it's not free, then of course not every abelian group possesses a structure of a module over some ring. A vector space over K is called a linear module over a ring in an algebra if we have a morphism from R, the ring for an algebra, to endomorphisms over K of V. So it means that in the above definition, to any A of R, we associate a linear map in V. A morphism of linear modules is a K-linear map, which commutes with the action of the ring or the algebra. Modules and linear modules over a ring in algebra is a category whose objects are modules and the morphisms are the corresponding morphisms. So this is a usual feature. Whenever we have some algebraic structures, if they are reasonable structures, we have a category of them. A vector space over a field K is a K module. If V is a module over, so V, vector space over K is a module over endomorphisms of K over K of V by definition, because we can act by endomorphisms of K on V. But if we have any subring of endomorphisms of V, then V is again a module over R. And there is a more general statement for any morphisms of rings from R1 to R2. If V is an R2 module, then it's also an R1 module, because we have the property of the composition, the transitivity property. First, we have a morphism from R2 to endomorphisms of V, and then from R1 to endomorphisms of to R2. So if we compose them, we'll obtain a morphism from R1 to endomorphisms of V. Later, when we talk about modules over a group or a K algebra, we'll usually mean a linear module as above over the same field. unless we specify something else. So simple modules and irreducible representations for rings and algebras are defined in the same way as for groups. So a simple module over a ring or an algebra is a module which does not possess any non-trivial submodule. And irreducible representation is those for which the module is simple. The last time we also proved the Schur's lemma, the lemma of Schur, which say that morphisms between two simple modules are either isomorphisms or zeros. And this is also true, we proved this for group, but this is also true for rings on algebras. In particular, if you consider reducible representation of a ring on V, its commutant, so the set of endomorphisms over K of B, which is commuting with the action of R, and we denote these endomorphisms over R of V, it's a division K algebra. So if it's not, then it has a kernel which must be a submodule. The submodule should coincide either with the whole V or should be zero. And both options, so that if it's zero, then the endomorphism is invertible. And if it coincides with the whole V, then endomorphism is zero. So it's either zero or invertible. So it means that every non-zero element in R prime defined like this is invertible. And it means that we have a division K algebra, which is not necessarily commutative, unless we have a field, an algebraically closed field. In general, R prime, the commutant of a representation, is just an K algebra. So it's not division. If we have an index, a possibly infinite collection of rings algebras and their modules, so Ri, Vi parameterized by I capital, such that Vi is an Ri module, the Cartesian product of them and the direct sum are modules over the Cartesian product of all rings. Just let me recall that the direct sum is a subspace of the Cartesian product for which only a finite number of components are non-zeros. So, and it's preserved by the action because zeros are preserved by the action of R. In particular, if Ri coincides with R for all I from I capital, so we have I capital copies of the same ring, then Vi, the Cartesian product, and the direct sum are modules over Ri, the product of I copies of R. But also we have a diagonal embedding of R into Ri, and it's a morphism of rings or algebras. Thus, the direct product and the direct sum are also R modules by the previous statement. So if you have a morphism of algebras or rings, and one is a and the module over the target, then it's also a module over the source. But there are also a variety of choices how to make a V I capital into a module over R. So for any index from I capital, there is a monomorphism from R to Ri, which associate to any I function which acts only as non-zero as A on K and zero otherwise. So if I is finite, we just put A on the ith position and zeros otherwise. And it's a morphism of algebra rings. So we see that the direct sum or the direct product of modules can be endowed with the structure of R module in I possible ways. And here above in N possible ways, if N is the number of elements in I capital. So that's a geometrical point of view of what is going on. So suppose we have an I family of rings or algebras parameterized by I, and modules Vi over each Ri. Then let's take the disjoint union of all Ri and consider the following projection map to any element AI of the disjoint union. It associates the corresponding index from I capital, and it's a projection, of course. And the same for V. So and now you see that an element in the Cartesian product of all R's is just a section of this I call this bundle, but it's not. Well, we call this a bundle, but it's not topological or smooth. And then if for any index I we associate some element in Ri, then we obtain an element in the Cartesian product. And the same for the model. So in fact, it means that Ri, so the product, the Cartesian product of RR acts on the Cartesian product of OV pointwise, so over each index. The diagonal embedding corresponds to the constant sections if OR is just just copies of the same R. Then the diagonal embedding is just constant sections. We have a map which associates to any I the same A in R. And the previous one, this one means that in fact we have a kind of delta function section. So this supported only the point I. Otherwise it's 0. And there are obvious topological smooth counterparts in the category of topological spaces or smooth manifolds. Otherwise, so in the category of smooth manifolds, we should consider the bundle of smooth bundle of algebra, smooth bundle of modules over each fiber, and then the sections of the first one will act on the sections of the second one. And in particular, see that functions on I on any set is a particular case of this one. So if R is a ring, Vi is a collection of modules over R, and W is also an R module. Then a multilinear map is a map from the Cartesian product of V's to W. It's called R multilinear if it commutes with the R action on each argument. It means the following, that phi of V1 and so on, A multiplied on the element in I's position and so on, Vm equals to A phi of the O M arguments. A ring A is called an R algebra if it is an R module and the multiplication is R bilinear. The polynomials, the ring of polynomials with coefficients in R is an R algebra. And if R is commutative, then matrices whose entries belong to R is an R algebra even. If R is a unitary ring, so it has a unit, then any R algebra is also K algebra because K is inside R. In general, for any morphism of rings, if A is an R2 algebra, then it's also an R1 algebra. So this is the same, the usual feature which appears for the morphisms. If something is an object of the target, there's also an object of the source. Okay, so let me talk now, come back to the representation theory in more details. So what are the general problems in representation theory? What we try to solve whenever we have some algebraic structure, a group, a semi-group, ring, algebra, and so on, and consider modules of the structure. Then we should somehow classify the linear representation, see how a general one looks like. Let us notice that isomorphic objects possess the same properties, so we can identify them completely. So it means that two isomorphic objects should be viewed as the same in a certain sense. So the problem is to classify representations up to isomorphisms. So let me give you a simple, very simple example, which everyone knows from the course of linear algebra. Let's consider polynomials with coefficients in some field k, kx, and let's consider linear representations of them on a k vector space V. Then it's sufficient to know how the generator acts. Acts like. For this, we need to choose some operator in endomorphisms of V. Impose that x goes to this operator A, and then every polynomial will go to the polynomial applied to an operator. For instance, the power of x will go to the same power of A, the sum to the sum, and so on. This is if V is finite dimensional, then of course this map from polynomials to endomorphisms of V is not a monomorphism, it has a kernel, and the kernel is generated by the minimal polynomial of the operator A. Now the problem how to classify representations of kx in endomorphisms of V, so only vector space V, is the same as how to classify linear maps with respect to the conjugation. So CA, C inverse, where C belongs to GLV. So this is the same as classifying of representations up to isomorphisms. And for a finite dimensional V over C, the answer is known as the Jordan canonical normal form, for instance, like this. So for instance, here we have a matrix 6 cross 6. All the entries lambda 1, lambda 2, lambda 3, all the eigenvalues belong to C. And there are several blocks. Some of them are diagonal. The first one is diagonal, and the other two are not. So A decomposes into these 3 blocks, corresponding to the decomposition of V into the sum of, so 6-dimensional, the sum of 1-dimensional, 2-dimensional, 3-dimensional spaces, such that each block belongs to endomorphisms of the corresponding space. So the first block is this one, so just multiplication on lambda 1. The second block is this one, lambda 2 on the diagonal, and 1 over the diagonal. And this third block is 3 cross 3, lambda 3 on the diagonal, and 1 is above. So given a linear module, another problem is how to decompose, if it's possible, into the direct sum of submodules as elementary as possible. And the simplest possible submodules are simple modules, of course, which do not have any submodules, any non-trivial submodules themselves. And they correspond to reducible representations. If a module decomposes into a direct sum of simple submodules, it is called semi-simple. And the decomposition is also called semi-simple. So in the previous example, the representation of Cx in 3-dimensional space, the first module is simple and the other two are not. So let me go this. So the first module, this one, just multiplication on lambda 1, is simple because it's 1-dimensional, it has no non-trivial submodules. And the other two, 2-dimensional, 3-dimensional, are not simple. So we have actually a chain of submodules for the third one, for the representation in C3. So C1 into inside C2, inside C3, which is V3. And for instance, on the block C2, A3 acts as the following matrix, lambda 3, lambda 3, 1. And it cannot be simple because there is a submodule, which is 1-dimensional, on which A3 acts like lambda 3. Let us note that both quotient modules C2 over C1 and 3C over C2 are isomorphic to the representation where the generator of polynomials acts as a multiplication by lambda 3. So there exists a short sequence of modules from C1 to C2 to C1 and C2, C3, C1. And this sequence cannot be split in the category of modules. For instance, if the first one is splitted, then the matrix must act diagonally, like lambda 3 on the first component of first summand and lambda 3 on the second one. But we know that the Jordan normal form is different. So this is one of the diagonals. So it means that it's not, it cannot be split into the direct sum of submodules. So it's different. It's not, this correspondence module C2 is not semi-simple. Let us use the following notation. For a module W, we denote by RW the sum of the R copies of W. So if V is a module which is semi-simple, so it splits into the direct sum of simple submodules, then we can use the following notation. So this is the direct sum of, if every submodule can be met only a finite number of times RP, then we can write it as follows. So this is a direct sum of RP, the multiplicity of a simple submodule, R row, the multiplicity of the simple submodule V row. And V row 1 and V row 2 are not isomorphic except if row 1 is equal to row 2. So there's a proposition which is quite nice, that the collection of simple modules V row in such a decomposition and the multiplicities R row are uniquely determined by V up to an isomorphism. So it means that if we have another decomposition of the same sort, that we can identify simple modules from the two, and the multiplicities will be the same. So let me prove it. So let us assume that V decomposes in a different way. So V the sum of R rho prime V rho prime, or some other set of indexes rho prime. So let us write in a row all representations. So it will be some lambda I and lambda I prime. And now we will try to identify them. So let's take V lambda 1 in the first decomposition and V lambda 1 prime in the second one. And let's consider the following composition of morphisms. So V lambda 1 is embedded inside V, and then it's projected to V lambda 1 prime by the projection onto the first, because we use the index 1, the first summand in the direct sum. V equals to the direct sum of R rho prime, V rho prime. So it's a morphism of modules. There are two possibilities. So first of all, just let me recall that both V lambda 1 and V lambda 1 prime are simple modules. So any morphism is either 0 or an isomorphism by the Schur's lemma. So the first possibility that V lambda 1 and V lambda 1 prime are not isomorphic. Then P1 prime restricted to V lambda 1 equals to 0. It means that V lambda 1 belongs to the sum of lambda prime not equal to lambda 1 prime, V lambda prime. So the kernel of P pi 1 prime. So finally, we'll find another index lambda prime such that V lambda 1 is isomorphic to V lambda prime. So here we the assumption is that the sum is finite. Otherwise, it's not like this. In general, it can be different. So okay, so it means that we can assume that V lambda 1 is isomorphic to V lambda 1 prime. Otherwise, we'll find another index. Then, if it's so, then there is an isomorphism of the rest of the summand, the sum of lambda for lambda not equal to lambda 1 V lambda, and the sum of lambda prime not equal to lambda prime V lambda prime. And this is given by the orthogonal projection, which is identity minus pi 1 prime. And then we proceed by induction, because now we have less elements in this direct sum. So it means that if we proceed by induction, we finally find one-to-one correspondence between modules and indexes. And then after that, also the multiplicities of simple modules. Another proposition is an equivalent definition of semi-simple module. So let V be a module over in R. So the following properties are equivalent. V is a sum of simple submodules. V is a direct sum of simple submodules. And every submodule W inside V is a direct summand. So it means that there exists a complementary of W inside V, such that V equals to W, the direct sum is W bar. So the proof, of course, it's easy to see that 2 is a particular case of 1. Let me prove that the first property implies then the second one. Let's consider the sum of all simple submodules. So okay, let's assume that V is the sum of all simple submodules. It's not necessarily direct. So let's take a maximal subset inside I such that the sum of Vj from J, where J belongs to J capital, is direct. So if the number of indexes is finite, it's always possible. If not, we'll use so we impose that the number of indexes I is finite. Otherwise, we have to use, and V is a finite dimensional vector space. Otherwise, we have to use the Zorn's lemma. So then this will become somewhat more complicated to prove, but not that much more complicated. So if everything is finite or finite dimensional, then we know that a maximal subset always exists like this. And also every module has a simple submodule. We just find the minimal one. For any Vk where k does not belong to J capital, there are two possibilities. either Vk intersected with V prime equals to 0, where V prime, as you see, the sum of all simple modules in the index subset J capital, and this sum is direct by the definition, because J capital is a subset, is a maximal subset such that the sum is direct. So that's the first possibility, Vk, where k does not belong to J capital. Then the first possibility, the intersection of Vk, V prime is 0. Vk is simple. The intersection can be either 0 or the whole Vk. The first possibility is 0. Then the sum of Vk and V prime is direct. And then J is not minimal. So it's forbidden. And the second possibility is Vk inside V prime. But then it means that all simple submodules Vk are inside V prime. Then it means that V actually is the same as V prime. And this is the direct sum of all submodules Vj, where J belongs to J capital. So V is semi-simple. And this is the direct product of direct sum of submodules, simple submodules. From 2 to 3, 2, it's a direct sum of simple submodules. 3, every submodule has a complementary submodule. So let's take some submodule W inside V. We use the same trick, and J is a maximal subset of A capital, such that V prime, which is the sum, okay, so V prime should be the sum of all Vj from J capital. The sum of W and this one, so it should be the sum of Vj, the sum of W and V prime is direct. The collection of those subsets is not empty, because if W is not V, there is at least one simple submodule which has 0 intersection with W. So J capital always exists, it's not empty. Now we do the same trick. So let's take a new simple submodule, and then it must belong to the direct sum of W and V prime. And thus, then V equals to W plus the direct sum of V prime, and W bar is exactly, the complementary is exactly V prime. And how to prove from this second statement, okay, it's wrong, from the third statement to the first one, of course. So consider the sum of all simple submodules of V. And we know that this sum is necessarily a direct sum. There exists at least one simple submodule by the finiteness assumption or by the Zorn's lemma. So it's not 0. At least there exists at least one simple submodule of V. So the sum of all simple submodules is a non-zero submodule. Possibly it coincides with the whole V, and that's what we want to prove. V0 is a semi-simple submodule of V. Then by the property 3, so the property 3 is this one, every submodule has a direct summand, has a direct complementary submodule W bar, such that V equals to W plus W bar. There exists V prime such that V0 plus V prime equals to V. If V prime is not 0, there must be at least one simple submodule V prime, but then by definition, it is in V0. So V prime is a submodule of V. Every submodule has a simple submodule, but all simple submodules are in V0. It means that V prime cannot be non-zero. It means that V equals to V0, which says that V is the sum of all simple submodules, or by the property 2 is the direct sum of all simple submodules. So any submodule of a semi-simple submodule is semi-simple. Let's assume that W inside V is a submodule and V is semi-simple. Let us prove that W is semi-simple itself. So we now use the same trick. So we take W0, which is the sum of all simple submodules of W. And now we want to prove that W0 coincides with W. Just again, by the above property, so we prove that the first condition is equivalent to the second one. So whenever we have a sum of simple submodules, we can choose a subset of indices such that V is a direct sum of simple submodules. And this follows just from the property of, from the simplicity of submodules. And we should use either the Zorn's lemma or the finiteness of, or the property of being finite dimensional. Okay. So now we do the again trick. We take a submodule in V, consider the sum of all simple submodules of W, and it's not empty because there are at least one simple submodule. And the sum of it, again, the sum by definition by the second property is semi-simple. By the property 3, because V, the module V is semi-simple, there is a property 3 which says that there exists W0 bar, the complement to W0 inside V, such that V is a direct sum of W0 plus W0 bar. It means that every element in V decomposes uniquely into the sum of two elements. One belongs to W0 and the second to W0 bar. In particular, this applies to all elements from W. So if we take any element from W, then we can uniquely decompose this element into the sum W0 plus W0 bar, where the W0 belongs to W0 capital and W0 bar belongs to W0 bar capital. But now let us notice that W0 is inside W because it's the sum of all simple submodules of W. It means that if you consider W bar, which is the difference between W and W0, then both elements W and W0 are inside W capital, because W small belongs to W capital by definition, and W small 0 belongs to W capital 0, which is a submodule inside W. So this also belongs to W, and the difference belongs to W. It means that W bar belongs to W. It means that we can always decompose every element in W capital into the direct sum of two elements, one of which belongs to W0, and the second to the intersection of W0 bar and W. Because W0 bar now belongs to W0 bar and W simultaneously. It means it belongs to the intersection. And why it's a direct sum? Because the intersection of W0 and W bar 0 is not 0. Sorry, is 0. It means that the intersection of W0 and the second intersection of W0 bar and W is also 0. So the sum is the direct sum. The decomposition of W is into the sum of W0 plus W bar 0 is unique. But let's consider the module W bar 0 intersected with W bar with W. It's a submodule of W, and every submodule has at least one simple submodule. But all simple submodules of this intersection are simple submodules of W. So by definition of W0, it must belong to W0 because W0 is the sum of all simple submodules. It means that, and the sum is direct, it means that the intersection of W bar 0 and W equals to 0. And for that, we obtain that W must coincide with W0, right? Because W0 bar is complementary to W0, W0 inside W, and W bar 0 does not intersect with W. It means that W must coincide with W0. It means that W is the sum of its simple submodules. It means that it's semi-simple. So every submodule of a semi-simple module is semi-simple. And also, if you have a submodule over a semi-simple module, then by the third property, third equivalent property, it has a direct complement. Let's call this W bar, which is again a submodule over a semi-simple submodule, and it is also semi-simple by the same proposition. But this complementary submodule is isomorphic to the quotient V by W. It means that not only every submodule, but also every quotient is semi-simple. The following simple corollary of the two previous propositions sounds as follows. So the notations are as above. The index set is supposed to be finite. There exists a subset I prime. So W is a submodule of V. Then there exists a subset I prime of indexes lambda prime inside I capital, such that W is the sum of simple submodules parameterized by this subset I prime. W bar is direct sum of simple submodules parameterized by the complementary subset I without I prime. And we have an isomorphism between W lambda prime and V lambda prime, and W bar mu and V mu for all indexes lambda prime from I prime and mu from I without I prime. So it means that if we have a submodule, whenever our module V decomposes into the direct sum, finite direct sum of simple submodules with some multiplicities parameterized by some indexes, and we have a submodule, then there is a complementary, and this submodule corresponds to subset of indices, and the complementary corresponds to the complementary subset. So we cannot meet anything else. And in particular, if V is a direct sum of the same simple module, then so it's the multiplicities R and V is R times V rho. Then every submodule is simply K times V rho, and the complementary is L times V rho, where K and L are multiplicities, so the non-negative integers, and their sum must coincide with R. So every submodule is some number of copies of the same irreducible module. Now we'll prove the last statement, which is called Jacobson theorem and then Wedderburn theorem, which are very important theorems for instant algebras, and they actually classify all simple algebras. Let V be a semi-simple R module and R be the commutant. So it means that R prime is all endomorphisms, all linear maps from V to V, which are commutant with the action of R. Then for any F from endomorphisms over R prime of V, so for any linear map which commutes now with R prime and any element V in V capital, any vector from V capital, there exists an element in R such that A V equals to FV. So what does it mean? So we have a module over R. R prime is the commutant, so this is the subset of linear operators commuting with the action of R. And it's an algebra, it's a K algebra. Now let's consider all endomorphisms commuting now with R prime. Of course, all endomorphisms coming from the action of R are commuting with R prime. So they belong to this. We call this endomorphisms R prime V. But the question whether it's the same. And now we'll prove that under certain conditions, it must be the same. If F is some endomorphism commuting with the action of the commutant, and V some particular vector, then F applied to V is A applied to V for some element from R. Let us prove this. The proof is not that tricky, but still kind of instructive. So let's consider the submodule R times V, which consists of all vectors of the form V applied to V for B elements in R. So this is the linear span of the vector V by the action of R. V is semi-simple by the third equivalent property. There exists a complement, or complement is not correct, so that V equals to RV plus the direct sum W. So the projector to RV, so this is the decomposition of a module into submodules. So the projector V to RV commutes with R. For that reason, it belongs to R prime. So it computes with the action of R. Simply, it's a projection to one of the submodules in the direct sum of submodules. It's easy to see that this must belong to R prime. And by the property of F must commute with all elements in R prime. It commutes also with F. It means that pi applied to FV is the same as F applied to pi V is the same as F of V. But this means that F of V belongs to RV, to the first summand in this direct sum. It means that there exists A from R such that F of V equals to AV. And this is what we wanted to prove. So for any vector V and any F commuting with the commutant of the R action, there exists A such that AV equals to FV. So we can generalize this statement. But before, let me show the following. Let V be a module over R, and R prime be the commutant as before. So these are all endomorphisms over R of V commuting with the action of R. Let us consider the n copies of V. So this is the direct sum of V plus V plus V and so on n times. And we already mentioned that this direct sum is again a module over R. So the action is as follows. So this is what we already considered before. So R acts on the direct sum as follows. So it acts component-wise in each component. So let's consider the commutant of this action over Vn. So if n equals to 1, we obtain R prime. But because R prime by definition is endomorphisms over R of V. But now let's do the same for the n copies of V. Then we want to prove that this is the same as the ring of matrices whose coefficients belong to R prime. So how this ring acts? So this means that for each T inside the commutant of the action of R in Vn, there exists a unique n cross n matrix which we denote Tij, all elements of which belong to R prime, such that T applied to the direct sum V1 and so on Vn is the following one. So this is T1j, the sum of T1j Vj, this is so on, the sum of Tnj Vj, or V1 and so on Vn, all possible tuples and tuples of elements from V. Any element of the direct sum of n copies of V. So the proof. So in general, of course, it's always true. I mean, it's always possible to find such a matrix. But this matrix will consist of arbitrary linear operators acting on V. So if you have the direct sum of vector spaces, then every linear apparatus decomposes into the is a matrix consisting of blocks. Blocks of operators. If V has a basis, so we identify isomorphisms, endomorphisms of V with matrices, then this will be a block matrix. It's just a usual feature. But in general, this matrix Tij consists of arbitrary linear operators acting on V. We have to prove now that these entries are not arbitrary, but operators commuting with the R action. So these belong to R prime, to the commutant. And indeed, let's take T from Rn, from the commutant over R of Vn. Then for any A from R and V1, so on the n tuple of elements, vectors in V, V1 and so on Vn from V capital, AT, V1 and so on Vn is by definition, this is the sum of A, T1j, Vj, and so on, A, Tnj, Vj. This is always true for any operator T. But as I said, the matrix Tij consists of elements of arbitrary linear operators in V. We have to prove that these entries belongs to R prime, so they're commuting with R. T applied to AV1 and so AVN is just the same, but instead of Vj, we put AVJ. So of course, if all entries Tij are commuting with A, the right-hand side of the upper line coincides with the right-hand side of the bottom one. So if ATij equals to Tij. So in one direction, it's easy to see that this is true. So if you want to prove this in the opposite direction, it's sufficient to consider vectors concentrated only on the ith position. So there's a vectors of the form B on the position I and zeros otherwise. And we'll have only one element in each component here, and they will be the same. And this will imply that A commutes with Tij for all A's from R, from the ring R. And this is the same as saying that Tij are elements of R prime, so the elements of the commutant. So in this, we want to use this simple statement, this simple lemma, to prove another theorem, the theorem of Jacobson, which states as follows. So V is a semi-simple module over R. R prime is the commutant. And this generalizes the previous lemma for arbitrary number of vectors in V. So for any F which belongs to endomorphisms over R prime of V, so those separators which are commutant with the commutant, sometimes it's called a double commutant, right? So R prime is the commutant of with respect to the action of R, and if we now take the commutant with respect to the action of R prime, we obtain something like R double prime. So there's all linear operators commuting with the action of R prime. So let's take F from endomorphisms over R prime of V, and or n tuple of vectors from V, which is arbitrary. Then there exists again A from R capital, such that AVI equals to FVI for all I from 1 to n. So before we had only for one vector, now we can prove this for n vectors. And the proof is simple. Actually, it's based upon the last lemma. So the direct sum Vn is again a semi-simple module over R, right? Because every V, every copy is a semi-simple. It's a direct sum of simple submodules. And the sum of, again, a direct sum, but just a bigger one of simple submodules. Let us consider Fn from Vn to Vn as follows, just as usual. It acts component-wise. So Fn V1 so Vn is Fv1, comma, so on, Fvn for all n tuples of vectors from V. So consider now the commutant of the action of R on Vn. As we have seen before, it's the ring of matrices with coefficients in R prime. F commutes with all elements of R prime, sorry. That means that Fn belongs to endomorphisms over Rn prime of Vn. And by the above lemma, there exists A from R such that AV1 and so AVn equals to FV1 and so FVn. So an R module is called faithful if the homomorphism from R to endomorphisms over K of V is injective, so it's a monomorphism. And now it's an important theorem of Wedderburn, which says the following. So let V be a simple faithful module over R. D is the same as R prime, be the commutant, and in this case, it must be a division algebra because V is simple. Then R is endomorphisms over this division algebra of V. It's a very important property. It implies that the double commutant of R coincides with R. So proof. Let's choose a basis of V over D. In fact, it's always possible to do that even if D is non-commutative, it's always possible to choose a basis. If D is commutative, then this is just a theorem from linear algebra. And A belongs to endomorphisms over D of V. By Jacobson theorem, there exists A from R from the ring such that A applied to EI, to all elements of the basis EI equals to A capital applied to EI for all I from 1 to the dimension up to the dimension of V. We suppose that V is finite dimensional, of course. Therefore, AV equals to A capital V for all elements V, right? If we have a linear operator which coincides on the basis, then it must coincide, right? Because every vector decomposes uniquely with respect to the basis. And then we use that A applied to the composition, to the linear combination equals to the linear combination A of EI, A applied to the basis. And this A small applied to the basis, basic vectors EI, the same as A capital applied to EI. It means that A applied to any vector is the same as A capital applied to any vector. And this means that A small coincides with A capital. It means that every A capital, which is inside the double commutant, coincides with some element A, which is inside R. It means that R coincides with the double commutant. It means that, the map, as we impose the map from R to endomorphisms over KV is injective. So it means that, in fact, R is the same as endomorphisms over D of V. So the corollary of the previous statements, so every simple finite dimensional K algebra is isomorph to a matrix algebra over some division K algebra. In particular, if K is algebraically closed, then A is isomorphic to the matrices n cross n for some n whose entries belong to K. So that's it's actually a very nice structure theorem for all associative algebras, rings. We know how simple objects are looking like. So they're just matrices, nothing else, with whose entries are in division algebras, maybe quaternions for real numbers. Then it's slightly more complicated, but still. But if the field is algebraically closed, they're just matrices, nothing else. First, let me show that matrices over D is simple, right? So that's, otherwise it doesn't make sense. For any division ring and any number n. Let us suppose that I inside M and D is a non-zero ideal. Now we have to show that I coincides with M and D. Take the following basis. So 1 on the i's position and zeros otherwise. It's a basis, it's just the standard basis of Dn, the n copies of D. Okay, so it's sufficient to prove that I contain will contain all elementary matrices Eij such that Eij Ek access Ei if j equals to k and 0 otherwise. So they are matrices such that on the intersection of eth row and j's column is 1, otherwise zeros. Let A be a non-zero element of I capital. Then AV equals to W for some non-zero vectors V in W. Right, so there's some non-zero vector V such that AV equals to W and W is not zero either, if A is not zero. Let's choose B and C inside M and D such that BW equals to EI and CEI equals to V. Then it's easy to see that the composition BAC equals to EIJ. So let's remark that C is uniquely defined, right? So because C is defined such that CEI equals to V. But B is not, because we require that BW equals to EI, right? When W is not an element of the basis. Here we just say that C applied to the basic vector EI equals to V, otherwise it's 0, it's uniquely defined. B is not, but however, W is a non-zero element, so it has n components in the decomposition with respect to EI, and at least one of the components assume that on the case position is not 0. Then in the basis E1 and so En, we can replace the vector Ek with W and we have a new basis. And now we require that B is fixed by the condition BW equals to EI, otherwise it's 0. And then it's uniquely defined. And just for in the linear algebra case, where D is just a field, is commutative, everything is simple, it's just a part of linear algebra course. Otherwise, we should be somewhat trickier because D can be non-commutative, but these theorems are working nice. So some theories about matrices, invertibility of matrices are working nice also for non-commutative division algebras. And the rest of proof is easier. If A is simple, then we take any simple module over R. A it always exists. We can take a linear left action of A on itself, then a simple submodule in it. V is a faithful module since the kernel is an ideal and A is simple. So the ideal is either OA is 0 or 0. It's not OA because the representation is faithful, so it must be 0. The representation is not 0, so it must be 0. Then the representation is faithful. For the Schur's lemma, D, the commutant of V over A, is a division K algebra. by the Verdi-Burns theorem, A coincides with endomorphisms over D of V, so the double commutant equals to the A. For any choice of a basis, we obtain a matrix, because whenever we choose a basis of V over D, then every operator corresponds to a matrix. It's usually in linear algebra. So we obtain a matrix algebra. If K is algebraically closed, then by the lemma of Schur, D equals to K. So there's only one possibility. Actually, if K is algebraically closed, the only possible division algebras over K are the only possible algebra is K itself. And then a semi-simple algebra is the direct sum of simple algebras. Each of them is isomorphic to the matrix algebra over some division. Okay, so this is all for today. Let me